Hello and welcome to the channel. Here is so-called homemade problem. However, it's hardly believable that no one else has ever come across it. So AD is the median of triangle ABC. We have another segment BE drawn from vertex B, where point E belongs to side AC, and point K is the point where segment BE meets the median AD. The ratio of segments AK and KD is M to N, where M and N are parameters whose values are known. And we need to find the ratio of segments BK and KE. I guess some viewers will try to find this ratio based on the ratio of areas, given that for two triangles having common altitude, the ratio of areas is equal to the ratio of bases. This is how my initial solution of the problem looked like, but then I found a shorter solution not related to the areas. For both way of solving, I needed a small auxiliary construction. So please pause the video and do it. Now let's compare the results. Let H be the midpoint of segment CE. Then DH is the midsegment of triangle BCE. Due to the properties of midsegment, DH is parallel to the base BE. Also, the length of DH is half the length of BE. Now consider triangles AEK and AHD. These triangles have a common angle with vertex A. Also, parallel lines DH and BE form equal corresponding angles. Therefore, the triangles are similar due to angle-angle rule, and we can equate the ratios of their sides. KE to DH is equal to AK to AD. Note that the length of AK is M units, while the length of AD is M plus N units. Therefore, the ratio AK to AD is M over M plus N. This allows to express the length of KE in terms of the length of DH. But the length of DH is half the length of BE. Hence, we can replace the length of DH by the length of BE, multiplying the denominator of the fraction by 2. So we express the length of segment KE in terms of the length of whole segment BE. Now we need to find the length of segment BK in terms of the length of BE, and this is really easy. We write that the length of BK is the length of BE minus the length of KE. Substitute the expression for the length of KE. Now the length of BE can be factored out, and we simplify the expression in the brackets. Now both two terms in the ratio are expressed in terms of the length of BE, so when we divide one expression by another, the lengths of BE are cancelled out. Moreover, the fractions have same denominators, which are also cancelled out. So we are only left with the ratio of the numerators, M plus 2N over M. This is the answer, but not yet the end of the video, because the obtained result has some interesting corollaries. Firstly, we can divide the obtained fraction term by term, from where we can see that the ratio BK to KE is always greater than 1, which means the segment BK is always longer than segment KE. Also, the expression shows that while m over n is increasing, the ratio bk over ke is decreasing. When m over n is 2, meaning that m is 2 times greater than n, point K is a centroid, the place where all three medians meet. In this case, the second term of the expression becomes 1. So the ratio bk to ke is also 2, which isn't really a surprise, as we expect segment BE to be a median as well. When m over n is less than 2, the ratio bk to ke is greater than 2, while when m over n is greater than 2, the ratio bk to ke is less than 2, but still greater than 1. The second corollary is even more peculiar. Take two vertices, for example, vertices B and C in triangle ABC, and draw segments BE and CF inside the triangle, where points E and F lie on the opposite sides. And K is the point where segments BE and CF meet. If K happens to lie on the median, then EF is parallel to BC. Indeed, since BE and CF divide the median in same ratio m to n, the ratio CK to KF is equal to the ratio BK to KE. Now consider triangles BKC and EKF. They have proportional sides and equal vertical angles between the proportional sides. Therefore, the triangles are similar due to side-angle-side rule, which implies equality of corresponding angles. In particular, angle KEF is equal to angle KBC. These are alternate interior angles for lines EF and BC, which are therefore parallel to each other. This completes the proof, and this is the end.